this is B. Naresh, working as assistant professor in EC department. And today's topic is problems on transistor fixed bias. So in this session, we are going to discuss the problems on fixed bias for an BJT. So we'll see the first problem. In a fixed bias compensation method shown in figure, a silicon transistor with current gain that is beta is 100 is used. So in that, they given some specifications like VCC is 6 volts, the collector resistance is 3 kilo ohms, and the base resistance RB is 530 kilo ohms. Draw the DC load line and determine the operating point and what is the stability factor. So for this problem, the given circuit is, and here the circuit is fixed bias configuration, means the transistor is biased with the fixed bias configuration, means that the base resistance is biased with a constant voltage source, that is from the plus VCC towards the base terminal. Under this biasing, we know that the potential drop between base and emitter, that is represented as VBE, and the potential difference between collector and emitter terminal, that is represented as VCE. For this problem, we need to find out the DC load line, and we also find out operating point. So means that based on that operating point, we need to identify that the transistor acts as a faithful amplification process. From that, we need to again find out the stability factor. So for this, to determine all these parameters like DC load line and operating point, first we need to identify the given data. So in that, the given specifications are the biasing voltage VCC is represented as 6 volts, and the collector resistance is 3 kilo ohms, and the base resistance is 530 kilo ohms, and the current gain is represented as 100. And apart from that, we know that here the emitter base junction is forward bias, hence across the input side, the forward biased voltage is represented as VBE. And we know that when the transistor is or emitter base junction is or a particular PN junction is a forward bias, the voltage across the PN junction diode is equal to cut-in voltage. Hence, from that representation, in this fixed bias configuration, the emitter base junction is a forward bias. Hence, the voltage between base and emitter VBE is also equal to cut-in voltage. And in the problem, they mentioned that the transistor is made with silicon. That is the reason. If the transistor is made with a silicon, the cut-in voltage is equal to 0.7 volts. From that representation, VBE is also represented as 0.7 volts. Now, first we are going to find out the DC load line. To observe this DC load line, so the DC load line is drawn with respect to collector current and VCE parameter here. That is the reason. We need to apply the KVL analysis at the output side. Means, so this is the output side, output loop. So it starts from the VCC node to the collector resistance and towards the collector terminal and towards the emitter towards lower potential. From this, we need to write the KVL expression. So if you want to write this KVL expression, the source is VCC, that is equal to the voltage drop across this collector resistance is represented as IC times the RC, along with the potential drop between collector and emitter is represented as VC. Hence, we represented as here VCC is equal to IC times of RC plus VC. And in that case, if you want to draw this DC load line, we need to identify the two parameters IC and VCE parameter. Hence, so here I consider that from this, I represented as this VC is equal to VCC minus, and this term I taken outside, hence the VC equal to VCC minus IC times the RC. In that equation, if uh, if we assume that the collector current is 0, means in this relation, if we assume that the collector current is 0, means VCC minus 0 times the RC, hence the VC becomes approximately equal to VCC parameter. That is the reason VC equal to VCC when the collector current is 0. And from the given problem specifications, in the problem, they specified that the VCC is a 6 volts, hence VCE equal to 6 volts based on the problem specification. And similarly, to draw this DC load line, we need to calculate again the collector current, how much maximum collector current is offered by using this fixed bias network. So hence, for the same relation, and from this relation, again, the VC equal to VCC minus IC times of RC. In that, here I am going to substitute at minimum voltage at when VC is 0. So what happens when VC is 0 by using this relation? That is 0 equal to VCC minus IC times of RC. From this, we need to find out the maximum collector current, that is represented as VCC by RC. Hence, the collector current is represented as VCC to the RC. Now we need to substitute the values. In a problem, they given that VCC is the 6 volts and RC is, so if you observe the problem, the RC is represented as 3 kilo ohms. Hence, so here RC is 3 kilo ohms. So kilo means 3 into 10 to the power of 3. So means IC becomes, so 3 1 to 3 and 3 to 6 means 2 milliamperes. The collector current is represented as IC is equal to, while you substitute this one, VCC is the 6 volts and the collector resistance is 3 kilo ohms. Hence, the collector current is represented as 2 milliamperes. So by using these two parameters, up to this, we observed that the collector current and the VCE parameter. So by using this, we can draw the DC load line. Now before going to that, again, now we are going to calculate the operating point, means at which point the transistor is acts as a perfect amplification process. So hence, for this case, we need to calculate the operating point. So to identify this operating point, we need to identify that again the VCE parameter in terms of this biasing, and again we need to calculate in terms of biasing, we need to calculate the collector current. So from this case, if you want to calculate the collector current, that is in terms of these biasing parameters, we know that the generalized expression is IC is represented as beta times of IB. So we need to calculate how much base current is flows with respect to these biasing resistances and biasing sources. Hence, here I apply the KVL at a input loop. So input means the starts from the VCC towards the base resistance and towards the base and towards the lower potential emitter terminal. And by using this input loop, if you want to write the KVL equation, that is VCC is equal to the voltage drop across this RB is represented as IB times of RB and directly connected to base, and base to emitter. In between this base and emitter, the potential is represented as VBE, hence I represented as VB. From this, we need to find out the IB value. So what is IB from this equation? The IB is represented as, it is a ratio of the potential difference between VCC and VBE to the RB. Now we can substitute the values. So we know that VCC is 6 volts and VB we assume that based on the silicon transistor when the emitter base is in the forward bias, and that is equal to cut-in voltage. Hence we consider as 0.7 divided by the RB value is, so that is 530 kilo ohms. So this is 530 into 10 to the power of 3. Hence 6 minus 0.7 divided by 530 into 10 to the power of 3. If you solve this ratio, it gives that the base current is 10 microamperes. So, and by using this base current, now we need to calculate how much collector current is the flows with respect to given the current gain of this bipolar junction transistor. Hence, to observe this collector current, we know that the collector current is represented as beta times of IB. And at this point, we observe that how much base current is the flows. So from that representation, the base current is 10 microamperes, and they given that beta is 100. Hence, I substitute here, beta is 100, IB is 10 microamperes, means 10 micro means 10 into 10 to the power of minus 6. If you solve this one, it gives that the collector current is 1 milliampere. Now similarly, we need to calculate the VCE parameter of for particular operating point. Hence, from that representation, the VCE is equal to, and we know that at the output side, the VCC is equal to, if you apply the KVL loop expression at the output side, VCC is equal to IC times of RC plus VCE. So from this relation, I observe that VC is equal to VCC minus IC times of RC. Now substitute the values here. So their VCC is 6 volts and IC just now we observed that is 1 milliampere, means 1 into 10 to the power of minus 3. RC in a problem they state that 3 kilo ohms, hence 3 into 10 to the power of 3. So this 10 power minus 3, 10 power 3 they get cancelled. 3 into 1, 3, 6 minus 3, that is nothing but 3 volts. So hence VC equal to 3 volts. So up to this point, we observe that VCE, this is VCE means VCE cube. This point is represented as VCE cube. So from the DC load line analysis, we observe that VCE is 6 volts, IC is 2 milliamperes. From the operating point, we observe that ICQ is 1 milliampere and the VCEQ is 3 volts. So by using these 4 parameters, we need to draw the DC load line and we need to represent the parameters. So hence, so from this operating point, VCEQ is 3 volts and ICQ is 1 milliamperes. Now I'm going to draw the DC load line. So if you want to draw the DC load line, so first we need to plot the characteristics between VCE versus IC. Let us take the x-axis is represented as VCE in terms of volts and the y-axis is represented as IC, that is in terms of milliamps. If you want to draw the DC load line, we need to locate the parameters VCE parameter and IC parameter. So we observed for drawing the DC load line, VCE is 6 volts, IC is 2 milliamperes. Hence, let us take this is 6 volts and let us take this is maximum is 2 milliamperes IC. Then to intersect these 2 points, 2 milliamperes along with the 6 volts, and this line is acts as DC load line. In that DC load line, we need to locate the Q point. So what are the Q point values? Just now we observed VCEQ is 3 volts, ICQ is 1 milliamperes. Hence, let us take this is 0 and this is 3 volts and half means this is 1 milliamperes, means this is the intersecting point. And this intersecting point, here it is called as Q point. So this is ICQ 1 milliampere. This is VCEQ is 3 volts. And in that again, they asked that to identify the stability factor for this fixed bias. We know that in a fixed bias, the stability factor is represented as S is equal to 1 plus beta. Hence, so in a given problem, they mentioned that the beta value is 100. Just you can substitute the beta value here. So S is equal to 1 plus 100, then it gives S is equal to 101 or 101. That is the stability factor of given problem by using the fixed bias. Now we'll see another problem. Find the collector current and collector to emitter voltage for the given circuit as shown in figure. For this given figure, let VCC is 9 volts, means this is the VCC. They given that VCC is a 9 volts and the base resistance is 300 kilo ohms and the collector resistance is 2 kilo ohms. And here this is the collector resistance, that is 2 kilo ohms. And the current gain of the transistor means the beta is, they mentioned that 50. Assume the transistor type is silicon, means that, so here the transistor is made with a silicon ends. So based on this representation, we know that if you want to observe the base voltage with respect to your emitter, that is represented as VBE. Based on this transistor type, we know that the VBE is 0.7 volts. Why? Because of that, here the emitter base junction is forward bias. Hence, when the particular PN junction is a forward bias, the voltage drop across the forward bias diode is equal to cut-in voltage. So similar to that, in a transistor, the emitter base junction is also forward biased. Hence, the voltage drop across this base terminal, that is equal to 0.7. Suppose if the transistor type is made with a germanium, you should assume here the VBE value is 0.3 volts. So from this given specifications, we need to find out the collector current and collector to emitter voltage. Means that we need to determine how much collector current is the flows and how much collector to emitter voltage, means that is represented as VCE parameter. So hence, first I'm going to find out how much collector current is the flows. To determine this collector current, we know that from the generalized expression by using the common emitter configuration, we know that IC is equal to beta times of IB plus 1 plus beta times of IC naught, or it is also called as ICBO. And we know that, and here this ICBO is called as reverse saturation current. If the reverse saturation current is much less than 1, IC is approximately equal to beta times of IB. So hence, first we need to determine how much base current is the flows with respect to the biasing specifications. Hence, we need to apply the KVL loop at the input side. And let's take this is the KVL loop equation from the input side, from the VCC to this lower potential. From that, we observe that the VCC is equal to the voltage drop across this RB, means that is represented as, so across this RB, the base current is the flows, hence it is represented as IB times of RB along with, and the potential difference between this base and the emitter is represented as VB. So from this, we need to find out IB. Hence, we know that IB is equal to VCC minus VBE by R. Now you can substitute the values based on the given specifications. So VCC they given that 9. VBE we assume that the transistor type is a silicon. Hence, the cut-in voltage of the forward bias diode is 0.7. And RB value is 300 kilo ohms. Hence 300 into 10 to the power of 3. So this is 9 minus 0.7 means 8.3 divided by 300 into 10 to the power of 3. That is equal to 27.67 microamps. So if you solve this ratio, it gives that the base current is 27.67 microamps. By using this base current, now we need to calculate how much collector current is the flows. By using this relation, what is the relation? IC is equal to beta times of IB. Hence, so by using this relation, just can substitute the beta value and IB value. In a problem, they mentioned that the beta means our current gain of this transistor is 50. Hence, I substituted beta is a 50. Just now we observed that the base current is 27.67 microamps. Hence, 27.67 into 10 to the power of minus 6. If you solve this one, it gives that IC is 1.38 milliamps. Means milli means into 10 to the power of minus 3. So this is collector current. And again in the problem, they ask that to observe to determine the collector to emitter voltage. Means we need to calculate this one. So collector to emitter voltage, that is represented as VCE. To observe this VCE parameter, we need to apply the loop analysis at the output side. We need to start from VCC to this lower potential. Hence, to determine this VCE or collector to emitter voltage, here you apply the KVL analysis at the output side. Hence, from this loop equation, we know that VCC is equal to, and the voltage drop across this RC is represented as, so across this RC terminal, it allows the collector current, hence it is represented as IC times of RC, along with the potential difference between collector and emitter is represented as VC, hence that is VC. So from this, we need to calculate. So from this relation, we need to find out VCE parameter. So how to calculate VCE? VCE is equal to VCC minus this term taken outside, hence IC times of RC. Now we got this, we know this VCC value, we got the collector current, and again we know that collector resistance value. Now we can substitute these values, hence VC is equal to, in a problem they mentioned that VCC is a 9 volts, and just now we observed the collector current is 1.38 into 1.38 milliamps, hence 1.38 into 10 to the power of minus 3. And the collector resistance is 2 kilo ohms, hence 2 into 10 power 3 means. So this 10 power 3 and 10 power minus 3 they get cancelled. Just can multiply and subtract from the 9. Then it gives that VC is equal to 6.24 volts. So here it is called as collector to emitter voltage based on a given biasing method. So that is VC is equal to 6.24 volts. Now we'll see another problem. The circuit as shown in figure has fixed bias using an NPN transistor. Determine the value of base current, collector current and collector to emitter voltage. The given specifications are VCC is 25 volts and a base resistance, that is RB, that is 180 kilo ohms, and the collector resistance, that is RC, is equal to 820 ohms, and the current gain of the given transistor is 80. So based on these given specifications, we need to determine the base current, collector current and collector to emitter voltage by using this fixed bias approach. Hence, first I am going to calculate how much base current is the flows. Then we need to determine how much collector current is the flows. Then we need to calculate how much collector to emitter voltage is generates with respect to your given specifications, like the biasing voltage is 25 volts and the biasing resistance at the base side is 180 kilo ohms and the biasing resistance at the collector side is 820 ohms and the current gain of the given transistor is 80. And here, and we need to identify the type of the transistor. They are not mentioned the type of the transistor. So we can assume either the transistor is made with silicon or a germanium. If the transistor is made with a silicon, then we need to assume that VBE is equal to 0.7 if it is the transistor type is silicon. Suppose if you are assuming the transistor is made with a germanium, and we need to assume this VBE is equal to 0.3 volts, and when the transistor is made with germanium, that is your choice. You can take anything, if the transistor is made with a silicon or a germanium. Now for this case, so first I am going to calculate or to determine the base current. So to determine this base current, we need to solve from this base current from the input loop. Hence, again we need to apply the KVL analysis at the input side or input loop. So we need to take from the source. Hence, VCC is equal to the voltage drop across this base resistance is represented as IB times of RB, along with the potential difference between base and emitter is represented as VB. Hence, I represented the VB. From this relation, we need to identify the base current. Hence, IB is equal to VCC minus VBE by RB. Now we need to substitute the VCC value and the VBE value and the base resistance. So here in a problem they mentioned that VCC is a 25 volts, and here I assume that the transistor is made with silicon. Hence the VBE is equal to cut-in voltage, that is equal to 0.7 volts. Hence 25 VCC is the 25 volts, VB is a 0.7. In a problem, the base resistance is mentioned 180 kilo ohms, hence 180 into 10 power 3. If you solve this ratio, it gives that the base current is 135 microamps, means that is equal to 135 into 10 to the power of minus 6 amps. Now, by using this base current in a problem, they are again asked that to determine the collector current. So, if you want to determine the collector current, the relation we know that for determining the IC based on the common emitter configuration, when the reverse saturation current is neglected, IC is approximately equal to beta times of IB. So in a given problem, the beta is mentioned, the current gain is 80, and IB just now we observed that is 135 microamps, hence 135 into 10 to the power of minus 6. If you solve this ratio, this product 80 into 135 into 10 to the power of minus 6, it gives the collector current is 10.8 milliamps. That is nothing but your 10.8 into 10 to the power of minus 3 amps. So just up to this point, we observe the base current as well as the collector current. Then we need to find out how much collector to emitter voltage is produces. Hence, to determine this collector to emitter voltage, that is the VCE parameter, now we need to apply the KVL analysis at the output side. So from this loop equation, again here, you remember this one, the potential difference between collector and emitter, that voltage is represented as VC. So from this loop equation, we know that VCC equal to the voltage drop across this RC is represented as, and across this RC, it allows the collector current, hence IC times of RC plus, and it is represented as VC. So from this, we need to find out the VCE, hence VCE is equal to VCC minus IC times of RC. So by using this relation, we need to substitute the given specifications, and we know that VCC is the 25 volts, and IC just now we observe that is 10.8 milliamperes, hence 10.8 into 10 to the power of minus 3. In a problem, they mentioned that the collector resistance is 820 ohms, hence this is RC value. Now we can solve this ratio, this product, it gives that VC is equal to, means collector to emitter voltage, that is 16.14 volts. So up to this point, in a given, based on the given specifications, we identified the base current, collector current and collector to emitter voltage. Now we'll see another problem. For a fixed bias configuration shown in figure, determine IC means collector current, and we need to calculate the collector resistance and the base resistance and collector to emitter voltage, that is the VCE, using the following specifications. And the given specifications are VCC is 12 volts, so this is the plus voltage, so means VCC is the 12 volts, and the voltage drop across the collector, they given that VC means the voltage drop across the collector is represented as 6 volts, and the current gain of the transistor is 80, and they given that the base current, that is equal to 40 microamps. So in the problem, they are not mentioned the biasing resistances, the values of the biasing resistances here. Means we need to calculate how much biasing resistance is required to allow the 40 microamps current at the base side. And similarly, we need to calculate how much collector current is allows with respect to given input current, that is 40 microamperes. through this biasing resistance, that is collector resistance, means we need to determine how much collector resistance is required and how much biasing resistance is required, means that is a base resistance, along with how much collector current is allowed with respect to your and the collector to emitter voltage, that is VCE parameter. So by using this fixed bias method, we need to determine these four parameters: IC, RC, RB, and VC. If you want to determine the collector current, we know that the relation based on the common emitter configuration, IC is equal to beta times of IB. So in this relation, if you observe this relation, beta is a known value. Why? Because of that, in a problem, they mentioned that the current gain of the transistor or beta is 80. And IB also mentioned the 40 microampere. Means we can easily calculate this, how much collector current is flows with respect to given specifications. Hence, first I am going to calculate the collector current. So just I recall this collector current expression. So this is the generalized expression. IC is equal to beta times of IB plus 1 plus beta times of ICBO. If the reverse saturation current is much less than 1, IC is approximately equal to beta times of IB. Hence, the collector current is represented as IC is equal to beta times of IB. In a given problem, beta is mentioned as 80 and the base current is represented as 40 microamperes. Just you can substitute this beta value and the base current here. So beta is 80, base current is 40 micro, means 40 into 10 to the power of minus 6. Then it gives the collector current is 3.2 milliamps. IC is represented as 3.2 milliamps. Now we need to calculate how much base resistance is required and how much collector resistance is required here. To solve this base resistance, you can apply the KVL at the input loop. So hence, so for this case, if you apply the KVL loop at the input side, so from this we know that the VCC is equal to IB times of RB plus, and in between this base and emitter, the potential drop is represented as VB. Hence, that is VB. From this relation, VCC is the known parameter, IB is a known parameter, VB is a cut-in voltage when the diode or when the emitter base junction is a forward bias. And here we assume that the transistor type is a silicon. Hence, the cut-in voltage or the base voltage between base and emitter, that is equal to 0.7 volts. So from this we need to calculate your RB value. Means how to calculate this is VCC minus VB, that is equal to IB times of RB. So if you want to calculate this RB, that is equal to VCC minus VBE by IB. Hence, so that is, sorry, here, so you can substitute here this RB. So just now we observed that RB is equal to VCC minus VBE by IB. So here the VCC value they given that 12 and VBE is 0.7 and the base current is 40 microamperes. Hence 40 into 10 to the power of minus 6. If you solve this ratio, RB value is 282.5 kilo ohms. So similarly, we need to calculate the collector resistance. So if you want to observe the collector resistance, again we need to apply the KVL at the output loop. So hence, to determine this RC, so here, so to determine this RC, just I can apply the KVL at output loop. So from this output loop, we know that the VCC is equal to the voltage drop across this collector resistance is IC times of RC plus, and this is VCE. But so at this point, and they given that the voltage drop across the collector is represented as Vc. Hence, I consider as Vc, or we know that VCE means the potential difference between collector and emitter voltage. Hence, can I write like this? VC is equal to VC minus VE. If you observe this configuration, emitter is directly connected to ground. Hence, the voltage drop across the emitter is represented as a zero. Hence, VC is becomes to your VC. So that is the reason. From that, here I represented as this is VC. By using this relation, now we can calculate this RC. RC equal to VCC minus VC by IC. Now can substitute the values here. So VCC is 12 volts, and the voltage drop across the collector they given that 6 volts, and the collector current is 3.2 into 10 to the power of minus 3. So based on this, the collector resistance is 1.875 kilo ohms. So this is 12 minus 6 divided by 3. Collector current is 3.2 into 10 to the power of minus 3. Just going to solve this ratio. It gives that the collector resistance is 1.875 kilo ohms. So apart from that, now we need to calculate the collector to emitter voltage VCE. So we need to calculate this VCE. So from this representation, we know that VCE means the potential difference between collector and emitter. From that statement, we can write like this: VC minus V means the potential difference between collector and emitter. If you observe this fixed bias configuration, emitter is connected to ground potential, hence the voltage drop across the emitter is represented as 0. So from this, VC is equal to VC, and the voltage drop across the emitter is 0, hence this is 0. So from this relation, VC is approximately equal to VC. So hence that is the reason I represented as VC is equal to approximately equal to the voltage drop across the collector. And in a given problem, they specified that the voltage drop across the collector is 6 volts. Hence, the VC is also equal to 6 volts. So up to this point, we observed some of the problems on a fixed bias by using the transistor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.